Welcome to an example in which we're testing about a linear relationship. A grocery store manager did a study to look at the relationship between the amount of time in minutes customers spend in the store and the amount of money in dollars they spend. The results of the survey are shown below. So basically, do customers, if they spend more time in the store, do they tend to spend more money in the store? That's the question. Is there a linear connection between the amount of time they spend in the store and the amount of money they spend in the store? So this would be like a marketing kind of question, right? People that are in charge of marketing, they would want to know, is there a connection here? So all kinds of people, real life, these are the kind of questions they want to answer. So how do we go about answering this? Well, they're asking, is there a relationship, specifically a linear relationship? So what we're going to look at is we need to go to the exam 4 notes. Let me show you. Exam 4 notes. Right here, and then go on down to number 6, testing linear correlation. That's what we're trying to test. I've got the notes already here for you. Now, how we know, by the way, look what they're asking. Find the correlation coefficient R, and then, and so that's what's going to key us in. Let me show you the notes right here. Here, testing linear correlation. So what do you do first? Put the data in L1 and L2, and then do a linear regression t-test. Okay, let's do it. So that's step number 1. So this is going to be your L1 data, and this is going to be your L2 data. So step 1, put the data down L1 and L2. Put the data down L1 and L2. All right, and then go to hit stat, go over to tests, go down to, what number is it? It is F on my calculator, probably same on yours. Linear regression t-test, and hit enter. You get all the information you need. It tells us the R, it asks you a bunch of questions. Let me give you those first off. It asks you for the X list and the Y list. That's just going to be L1, L2. It's probably already there on your calculator. You don't need to do anything. Frequency 1. Then it has this funny looking B, which is actually a Greek beta. And funny looking P, which is a Greek R, really, Greek rho. And then it has not equal to 0, less than 0, greater than 0. All right, so what do we choose? So again, L1 here, if it's not already there, just hit second and 1, and L2, second and 2, but it's probably already there. All right, and then frequency is always 1, and then we're going to choose not equal to 0. Why? Because that's what they have right there, not equal to 0, right? All right, so hit enter, get your numbers, and when you do, I'm getting an R value that is, and how many decimals? I don't really say. 2 decimal places. So I'm getting an R value right here, 0.85, rounded 2 decimal, 0.85. And then, an HO and H1. What are my HO and H1 going to be? Well, it's going to be rho. So we're going to say the Greek. Now you might wonder, why isn't it just R? Well, the thing that looks like a funny looking P is actually a Greek letter. It's a Greek R called rho. So I know it looks like a P, but it's a Greek R, and so that's what we want to use. Why? Remember, the Greek letters are always the true value for the whole population. It means R for the whole world. No, because that's what we're trying to figure out. We're trying to say not just for these. What is this? 1, 2, 3, 4, 5, 6, 7, 8 customers. Not just for these 8 customers. We really want to know. The marketing people want to know for the whole world. Is there a connection between time spent in the store and money you spend for the whole world, not just for these 8 customers, right? And so this R value is English. Whenever you have an English letter, that always means just for the sample. just for those 8 customers, how linear is their connection? Remember, R is a measure of linear connection, right? If we were to graph these points on an XY axis and get some dots, how much would they fit a line? How well do they fit a line? That's what R tells us, is how well they fit a line. Remember, R goes from -1 to +1 with 0 in the middle, R does. And the closer you are to -1 or +1, the more you're a line up or down. Whereas if you're around 0, there's not much evidence that you're a line. 0.85 is pretty good. That's close to +1. So, in other words, that means these dots, if you put them on a graph, they line up pretty much. They seem to go upwards like a line. This data. You understand what I'm saying? If I was to graph this data over 10 up 1, over 10 up 1, and then over 26 up 250, over 26 up 250, and the dots would pretty much fit a line pretty closely. It seems like there's a linear connection. The more time you spend in the store, the more money you tend to spend. That's what this R is telling us. It says for these 8 customers, for this sample, the linear correlation coefficient is 0.85, meaning there's pretty strong, that's close to 1.0. Remember, R goes from -1 to +1 with 0 in the middle. So if it's close to +1 or close to -1, +1 is a line up. -1 would be a line down. So our line seems to go up, meaning more time, more money. More time in the store, they spend more money. There's 0.85 is about right here. It's pretty close to 1. Seems like there's strong evidence, pretty strong, that there is a linear connection here. If you can just keep people in your store longer, they're more likely to spend more money. Pretty strong evidence. But what we really want to know is what's the truth for the whole world? What's the Greek R called rho, which looks like a P, right? This sample of 8 customers, great, yeah, they had some evidence, but does the whole world, is there evidence for the whole world? That's what you think, well, yeah, that's what this sample is, right, but maybe it could have been luck. What's the chance of that? Well, that's our p-value, and so we'll get that right there. Where's the p-value? There it is. I got the p-value, and they want 4 decimal places, so I got 0.0073. That's pretty low. Then it says alpha 0.05. So p-value 0.0073. How does that compare to alpha 0.05? Remember what they're saying. They're saying, okay, yeah, you did these 8 customers, and they had a pretty strong linear correlation coefficient. It looks like there's strong evidence they fit a line, but maybe that was just a lucky 8 customers, and that's really not true for the whole world. That there really isn't a connection between time and money for the whole world. Maybe not. How do we know? Because maybe this could have just been a lucky 8 customers. What's the chance of that? Well, that's what the p-value is. It's the chance you just got lucky numbers, which is very low. It's under 1%, right? 0.0073. That p-value is very low. It's less than the alpha level. So remember what that means? If the p is low, then the HO must go. Go what? Go away. Right? Remember the saying, if the p is low, the null must go. Yeah, our p is low. It's less. It's really, there's a very low chance that this is just a lucky 8 customers. No way. Those dots really seem to line up, is what that study is telling us. The chance of luck is super low, less than a 5%. They wanted us to test at the 5%. They wanted less than a 5% chance of luck. That's the level of significance, and we got it. We got a really low chance of luck. So the p is low, the null must go. Bye-bye, null. Cross out the null. We're keeping h1, which means what? The rho, which is the Greek r, does not equal 0, meaning it's not 0. The rho, same thing, it's the Greek r, is not 0, meaning there is a linear connection. Linear, right? Because if rho is not 0, and if rho is 0, that would be not linear. That's what HO equals 0 means, not linear. But we're not going with that. We're going with this one, linear, because we're saying rho is not 0. If rho is 0, that means there's no linear connection. But if rho is not equal to 0, there is a linear connection, and that requires strong evidence, doesn't it? You know, the null always is weak evidence. but we didn't go with that. We went with the strong evidence of a linear relationship. Why linear? Because the rho, which is like the r, is not 0. We're saying there's strong evidence that the true r, the Greek r, is not 0. Which means if it was 0, if the rho was 0, that would be no linear relationship. But we're saying, no, there's strong evidence of a linear relationship because rho is not 0. All right, let's see that conclusion here. There is statistically significant evidence. Yeah, strong. That's right on the money. Let me get a new color here. It's statistically significant. Yes. How about this one? Insignificant. No. Significant. Yes. Insignificant. No. So it's one of those two significant. Which one? To conclude that there is a correlation between the amount of time customers spend at the store and the amount of money that they spend at the store. Thus, the regression line is useful. Yeah, that sounds good. Boom. What did the other one say? Statistically significant evidence to conclude that the customer who spends more time at the store will spend more money than a customer who spends less time at the store. Thus, the regression line is not valid? No, the regression line is valid. There's the mistake on that one. All right, and what's our r squared? That's on your calculator as well. R squared, mine, 2 decimal places, is 0.725, so 73. And what does r squared mean? Well, I haven't told you about r squared before now. Here's what r squared means. It's a 73%. So what is this 73? Now this means, if you change it to percentage, 73% of something, of what? 73% of all customers will spend an average amount? No. There's a 73% chance that the regression line will be a good predictor of the amount of money spent at the store based on the time spent, or 73% of the variation in the amount of money that customers spend in the store is connected to the amount of time they spend in the store. That's it. Yeah. What the r squared variable tells you is how much one variable affects the other. In other words, people spending more time in the store tends to make them be connected with them spending more money in the store. But that's not the only thing, right? It isn't just time, right? What else? Well, whether you're having a really good sale, or whether you have certain items they want, or on and on the list goes. There's other things other than just time in the store that affect how much money people spend. Well, right, okay, but time in the store is one of the things that affect it. They have a linear connection, yes. In fact, there's strong evidence that there's a linear connection, that time does affect it. How much does it affect it? Because it's not the only thing. What percentage of the effect on money is time? In other words, time is what percentage of the effect. That's what r squared is. It tells us that 73% of the variation of the change in the amount of money that customers spend is connected to the amount of time. 73% of what they spend is determined by how long they're in your store. That's what r squared tells you. R to the second power tells you. It's very interesting. It tells you how much of one variable affects the other. Money that they spend in the store is 73% affected by how much time they spend in the store. Then the other 27% is affected by other things. Then they ask for the equation. So that's right on your calculator. If you notice, your calculator will say y equals a plus bx. And it'll tell you that so this is the a plus bx, right? And it tells me, I'm looking at the b and they want 2 decimal places. The b I'm seeing is 11.33 and the a is negative 70.77. Right. Okay. And then it says now, that's the linear regression equation. Use the model to predict the amount of money spent by a customer who spends 20 minutes at the store. If you answered on part C, the use regression line is not valid, then put in D and E here. No, we didn't do that. Part C, we didn't say not valid. We said regression line is useful. So we need to answer. So in other words, if somebody spends 20 minutes in the store, how many dollars are they going to spend? 20 minutes in the store. How many dollars, right? Time in the store should tell you something about money they're going to spend. Well, how do we know that? Well, that's what this equation is. This linear equation right here connects time in the store with money they're going to spend. How do you know which is which? Well, remember up here, the the X list is L1 and the Y list is L2. So this is X and this is Y. X is time, Y is money. X is time, Y is money. X is time, Y is money. So let me come right here and go X is time, Y is money. So if they spend 20 minutes, we're going to plug in X is 20. So I'm going to take the equation. I'm going to go equal, I'm going to go, let me get this out of the way. I'm going to go Y equals negative 70.77 plus 11.33 times 20. See how I plugged in 20 for X right there? Plug in 20. Plug in X equals 20 to the equation. That's what you do. This equation this equation here is a connection between X values and Y values. So if X is 20 minutes, if they spend 20 minutes in the store, this equation can be used to tell you how much they're going to spend. So let's do it. I'm going to use that equation now. So negative 70.77 plus 11.33 times 20. I'm getting Y equals, let me go back. It came out to be 155.83. They're going to spend, round your answer to the nearest whole number. Oh, they're going to spend $156. So they just want me to round to the nearest whole number of dollars. So they're going to spend about $156 if they spend 20 minutes in the store. Do you see how that worked? This equation, that's why we do, this is why people care about this kind of statistics in the real world. This equation that we got from this table connecting time with money is a connection equation between time and money. So you can plug in time and you'll get money on average. So if a customer spends 20 minutes, on average they're going to spend $156 in your store. Interesting. Now what does this actually mean? It says interpret the slope. Oh, now what's the slope? The slope equals number next to X. Do you remember that? Slope is the number next to X. What's the number next to X? 11.33. What is that? Well, it's a slope. What is a slope? Slope, remember what we talked about that? Slope is rise over run. Slope is rise over run. You want to remember that from algebra? You need to know that slope is always rise over run. And so then I take that 11.33 and put it over 1. Why'd you put it over 1? Well, because it doesn't change it, right? 11.33 divided by 1 is still 11.33. If I divide it by 2, that'd be a different number now, right? That'd be half of 11, 5 point something, right? But if you put 11.33 over 1, you haven't changed it. Yeah, but why do you want it? Well, because I have to think of it as a fraction. Why? Because that's what slope means. Slope means rise over run. So you've got to look at that 11.33 like it's a fraction. So it's 11.33 over 1, which hasn't changed anything, but now it looks like a fraction. So rise, and what is rise? Rise is y values, right? Right, in a graph, up is y values, run is sideways, x values, rise is up, is y values. So this is therefore y values over x values. And what are y values? Let's go back. Y values are money. X values are time. So y values are money. And x values are time. So all of this is to say, are you getting the real life meaning here? This 11.33 is dollars and the 1 is time. So in other words, $11.33 for every 1 minute, time, right? Minute in the store. Every 1 minute they spend more in your store, on average they're going to spend $11.33 more. That's what that slope means. That's what the slope of this linear regression equation means. Why? Because slope is rise over run. So 11.33 over 1 every minute. So let's see, for every additional minute, they tend to spend on average 11.33 more. Yeah, that's exactly it. What do the other options say wrongly? The slope has no practical meaning. No. As x goes up, y goes up? Well, yeah, but we can be more specific than that. Because the p-value was greater than the significance level, the use of the regression line is not valid. No, the p-value was not. We're good here. And then it says, interpret the y-intercept. What's the y-intercept? Well, the y-intercept is the number not next to x. It's the number not next to x. So what is that in this case? It's the number not next to x. So that's the negative 70.77. So what is that? The average amount of money spent? Is that? No, it's not that. What about the next thing? If a customer spends no time at the store, they'll spend negative 70.77. Well, I mean, that really can't be the case, can it? Is that making sense? How can you spend negative amount of money in the store? That can't be. Can it? Right? You can't spend negative money. The best prediction for a customer to spend no time in the store. No, you can't spend it because the p-value is greater. It wasn't. The y-intercept has no practical meaning. Yeah, there it is. In this one, there's no meaning. That negative 70.77 has no meaning, no practical meaning in the real world. But the slope did. The slope definitely had practical meaning. So there we go. We get a lot out of that connection. There is strong evidence that time spent in the store is money. In fact, it's $11.33 for every minute. That's what the slope means. Slope is rise over run. $11.33 every minute, and if somebody spent 20 minutes, they would spend on average $156.